In this video, we'll cover the Nutrient Removal Wetland tool. Nutrient removal wetlands are off-site methods to reduce nitrate from tile-drained water. Therefore, they get placed below tile-drained fields. Thanks to Iowa's CREP program, we have some general siting criteria that we follow. The criteria that we use includes having a collective flow path of at least 60 hectares or approximately 150 acres. And it can't be any larger than the total watershed drainage, which makes a lot of sense. The pooled area and drainage area ratio must be between 0.5 to 2%. The buffered area to pooled area ratio has to be less than 4. And bank height cannot exceed 4 meters. Optionally as well in the tool, you can choose to avoid streams and roads, which is highly recommended. You're not going to build a wetland that is going to flood out a roadway, and you don't really want it to flood out a stream either. Alright, so let's go ahead and run the tool. It can take a while, so if you're doing this along with me, I recommend starting it now. So we'll go to our toolbox, go to the impoundment siting tool set, and choose the first tool, Nutrient Removal Wetland. As we can see, we have quite a few inputs we have to enter here. First off is the unfilled DEM. Then we have our D8 flow direction raster, our D8 flow accumulation raster, the watershed boundary, and here's those two optional inputs, the stream reach and then a roads layer, both polylines. Again, it's highly recommended that you do include these. And then we have our Z factor, and then this variable spacing, which will be the distance between sample points when it's being tested to see if a nutrient removal wetland would be ideal for that location. The spacing options that we supply are 100, 150, 200, and 250 meters. The smaller the spacing, the longer it's going to take for the tool to run because it's testing more sites. And then the larger the spacing, it's just the opposite, the quicker the tool will run. However, the smaller the spacing also means that more sites will be tested, so you may potentially get more outputs. We then have the wetland impoundment height in meters. We recommend 0.9 as the default, however you can choose a range between 0.6 and 1.2 meters. And then the wetland buffer height also in meters. We provide a default of 1.5 meters. You may choose between the range of 1 to 1.6 meters based on your local knowledge. And the two outputs we get are the nutrient removal wetland polygon, which will have our wetland pool and wetland buffer shapes, and then the output drainage area for the nutrient removal wetland. So we can see that the total area that the wetland will actually treat. So let's go ahead and add these in there. We'll start with our unfilled DEM. It's the new DEM. So grab and drop that in. You can see some have been automatically populated. I am going to include my stream reach. I don't want any cited along that line. Unfortunately, I do not have a roads layer right now, but if you do have one, I highly recommend that you put it in. You'll see that I am going to get some wetlands that probably cross over a road, and that's just not ideal. We would never build a wetland that could do that. You can get a roads layer from any like county data source or statewide data source from the DOT or something like that. They're pretty widely available. And then our Z factor, for me, 0.01. Spacing, just for the sake of the training, I am going to go with 250, but feel free to choose whatever you'd like. I'm going to keep these defaults. And then we make sure that they're going in the right place, which they are, so we hit OK and let it run. While the tool is running, I'm going to go over what it's actually doing. So first off, the sample points are placed at whatever spacing you chose. So for me, 250. So points are generated along concentrated flow paths every 250 meters. A 20-meter buffer is then placed around those sample points, and then the highest elevation in the buffer represents the top of the bank. The second step is to define the drainage area to each sample point. And then within that drainage area, the DEM will be reclassified to show the wetland pool and then the wetland buffer. We then need to test the site for suitability. We'll have to make sure that the wetland to drainage area ratio is still between 0.5 to 2%, and that the buffer is less than 4 times the area of the wetland. If the site was found to be unsuitable, it's thrown out, and then the next point upstream is sampled. So you can see there that that point is literally just the next one upstream. But if it is suitable, that point is kept, and we move to the next point that is outside of that wetland buffer area. Alrighty, and my tool has just finished running, so let's go ahead and take a look at our results. You can see we have our nutrient removal wetland polygon that was output, and then the associated drainage areas as well. I'm going to rearrange these, and before we go and symbolize them, let's take a look at our attribute table. So at first you may think that you have 102 ideal sites for a wetland. But if you take a closer look at your attributes by the site ID, you can see that we have duplicates. And that's because with each item in this attribute table, one accounts for the wetland pool area, and then one is the wetland buffer area. And they both have the same site ID because they're associated with the same site. You can see that these other attributes also repeat themselves. We have the contributing area in hectares to the wetland, we have the pool area, hectares, and then we have that vegetative buffer area. Then the stream elevation, bank height, bank elevation, and then we have, again, specifically for the pool, a storage in acre feet, and then a variable storage. So this is including that wetland buffer now, also in acre feet. So now that we understand how our output is built, we can go ahead and re-symbolize it. We'll go to symbology and then go under categories and then unique values. Let's symbolize it by covered type. I'll hit add all values. And after this is done, we'll be able to see where our buffers are and then where the pool is located. So I'll make this blue, hit apply, okay. And then I'm also going to go into my drainage area and re-symbolize this. I'm also going to change the transparency. So you can see they take up quite a bit of space. So I would like to be able to see what's behind them. We'll hit apply, okay. And now we get an idea of what portion of the wetland is an actual pool, which portion is a buffer. So yeah, you get an idea of the actual structure of the wetland that would be built here. I'd like to take a look real quick at these three right here. They tend to feed into each other. We can see that they're following the same concentrated flow path going along here. In this case, you probably wouldn't build these two that are further upstream. You would build the one that's furthest downstream. And that's because this furthest one downstream is going to treat the same area as these two up here. So it's just good to be conscious of your outputs. You see same thing along here, even here. Any ones that are upstream of each other, you would want to petition for the furthest one downstream first because it's going to treat all of this area upstream of it. So here's a brief recap of the nutrient removal wetland tool.